This section explains why network science begins by throwing away what its nodes are made of. Strip away what the nodes are: genes, routers, people, generators, and what remains is a wiring diagram, obeying the same laws across every domain. That erasure is the chapter's whole move. Universality purchased by forgetting the substrate, the same trade that made statistical mechanics work. The Northeast blackout of 2003 is the anchor. A fuse in Ohio darkens Toronto because links make failure non-local. Interconnectivity is one mechanism read with two signs. Cheap electricity and cascading collapse are the same property. The book's arc falls straight out of it. Map the structure, model the dynamics running on it, then ask how their interplay fixes robustness. Two enablers, not one insight, opened the field. Network maps became obtainable, and the maps looked alike. This section explains what graph theory does to a problem once the problem is drawn as nodes and links. Euler proved the 7-bridge walk impossible by counting odd-degree nodes. The verdict came from the graph itself. No amount of searching harder would have produced it, and that inversion is what the chapter is for. Once a system is stripped to nodes and links, its possibilities become properties of structure, immune to cleverness. Everything built afterwards is measurement apparatus for that one claim: degree distribution, the adjacency matrix, distance, components, clustering. This is the vocabulary in which a graph of 1,000,000 nodes becomes sayable at all. The boundary sits at the choice of what a link means. Coworkers, friends, and lovers give 3 different graphs of the same people, and graph theory says nothing about which one to draw. This section explains the Erdős-Rényi random network, the model that is built to be wrong. Placing every link by an independent coin flip fixes the whole architecture from 2 numbers, the number of nodes, n, and the connection probability, p. Everything else follows from those 2. 4 consequences come out. Degrees are Poisson distributed. A giant component appears the instant the average degree passes 1. Distances shrink like the natural logarithm of n divided by the natural logarithm of the average degree. Clustering equals p. The cocktail party carries the intuition strangers are connected long before they have met, so mere randomness already buys global reach. Then 2 predictions survive, contact with data, and 2 collapse. Real networks are indeed small worlds, but their degrees are not Poisson, and their clustering does not vanish with size. The chapter's place in the arc is to serve as the null model whose residual is the phenomenon. What the random model fails to predict is exactly what needs explaining. This section explains what happens to a network when its degree distribution loses its scale. Randomness has a size you can quote: the Poisson mean is a characteristic degree, and every node sits near it. This chapter dissolves that. The World Wide Web's degrees fit a power law, where the probability of a node holding degree k falls off as k raised to the power minus gamma. A power law names no characteristic size, so the average degree stops being representative of anything. Hubs are then the distribution's own tail, expected rather than forbidden. The largest one grows as n raised to the power 1 over gamma minus 1, polynomially with the size of the network, where a random graph's biggest node crawls at the natural logarithm of n. That single move is what the chapter is for in the book's arc. Barabasi puts it plainly in Chapter 4, no matter what network property we are interested in, from communities to spreading processes, it must be inspected in the light of the network's degree distribution. This section explains where scale-free structure comes from once you already know it exists. Chapter 4 established that real networks are scale-free. This chapter supplies the generator, and the shift is from topology to history. A degree distribution gets deposited by a process rather than drawn from an ensemble. 2 ingredients, each one a hidden Erds, Renyi assumption broken. The node set grows, and every arrival attaches with probability linear in existing degree, pi of k equals k divided by the sum of all degrees. Rich gets richer, follows, and with it, gamma equals 3. Fixed, uninvited, nothing left to tune. Hubs are simply the early arrivals. Age is the concealed coordinate behind degree. The claim underneath, convergence of the World Wide Web and the metabolism onto one architecture, requires no shared substrate, only a shared mode of assembly. This part explains why a network's degree distribution records the history of its growth. A network is a film rather than a photograph. Barabasi's chapter turns the degree distribution into a fossil of how the network grew, and the power law becomes the residue of 2 mechanisms running in time. The primitive is growth plus preferential attachment. Nodes arrive one by one, and each new node links to existing nodes with probability proportional to their current degree. Rich get richer. With a temporal twist, early nodes accumulate for longer, so degree is a clock. The static random graph tradition asked which wiring is likely and got Poisson. Asking instead which wiring is reachable by this process gets a power law exponent, gamma equals 3 for free, with no tuning. Both ingredients are necessary, and neither suffices. Growth without preference gives exponential degrees. Preference without growth eventually connects everything to everything. The scale-free state is a dynamical equilibrium rather than a configuration. This section explains why fixing a network's degree distribution leaves its wiring undetermined. And what second-order quantity closes the gap? Angelina Jolie marries Brad Pitt. Yeast's 2 largest proteins refuse to touch. Same scale, free degree sequence, opposite wiring, so the degree distribution pk does not determine a network. What stays free once the degrees are fixed is how degrees pair across a link, and the chapter's move is to measure that freedom as deviation from a factorized null. The joint quantity Eij, the fraction of links joining a node of degree I to a node of degree j, is set against the product of its own marginals, Qi times Qj. Equivalently, the observed count of its own marginals, Qi times Qj. Equivalently, the observed count of hub-to-hub links is set against the chance Q prime divided by twice the number of links. L. Weight on the main diagonal is assortative. Weight on the secondary diagonal is disassortative. Neither of these is the neutral case. This is the connected correlation mu. Subtract the product measure, keep the residue. It is installed here as the second-order statistic the book needs before robustness and spreading become predictable rather than assumed. This section explains why network robustness behaves as a phase transition rather than a design property. Remove a fraction f of nodes at random, and the giant component holds together until a critical value fc, where it vanishes all at once. The Moloyan-Reed criterion fixes that threshold entirely through a single quantity, kappa, defined as the average of the squared degree divided by the average degree. Kappa is one ratio drawn from the degree distribution, blind to everything else about the wiring. That single quantity carries the whole argument. Every robustness question collapses into a question about the second moment of the degree distribution. For a scale-free network whose degree exponent gamma is less than 3, that second moment diverges. The critical fraction Fc approaches 1, so random failure never fragments anything. The same hubs that grant the immunity make targeted attack lethal. This section explains why community structure is invisible to the degree distribution and what the chapter stakes on that gap. Chapters 3 through 6 characterize a network by P of k, the probability that a node has k links. Two networks with identical P of k can differ entirely in who connects to whom, and community structure lives exactly in that residue. The chapter's fundamental hypothesis says the mesoscale is uniquely encoded in the wiring diagram and waits there to be found. That claim, plus 3 more, gives the chapter its whole content, connectedness and density. Randomly wired networks have no communities, and maximum modularity picks the true partition. Every algorithm is a wager on some subset of 4 unproven hypotheses. The closing admission sharpens it. Algorithms identify communities, whether they are there or not. So, the ground truth a detector reports is partly its own construction. This section explains how a spreading process behaves once you restore the contact network that classical epidemiology throws away. Classical epidemiology buys its solvability with homogeneous mixing. Everyone contacts everyone, so only the average degree survives. Restore the contact network, and one quantity changes the physics. The epidemic threshold becomes mean degree, divided by mean squared degree. On a scale-free contact network, the second moment diverges, so the threshold vanishes and the characteristic time with it. An arbitrarily weak pathogen persists and reaches most of the population almost at once. The classical control move, pushing transmissibility below threshold, loses its target. Here, the book's structural machinery cashes out as dynamics. The Metropole Hotel physician is a hub seen by a process, and a spreading process reads degree heterogeneity, where the averaged model saw a mean.